Alright, hi y'all. Today we're going to be going over the single time constant amplifier circuit. Now in class we've gone through everything that we will be able to learn for this topic, so this is more of practice for I guess any upcoming exam or quiz. And this was taken from a previous exam, so this would be the caliber type of question we will see. So let's get started here. So we're given this amplifier circuit and we're asked to find V out over V in, or our transfer function. And we have to write it in a form that is easily identifiable for our poles and zeros. That way when we draw the Bode plot, it's easy. So here we can first identify what? Well, we have two stages. We have our source stage and we have our first stage, or output, our output stage. Now, what this means is we're going to be using the output of our source as an input for our output stage. So that's essentially what amplifier circuits are. So let's get started in solving it. So one thing we'll notice is these two circuits, they depend on two different values. Something that we'll need is we need to solve for V out over V in. That's our final destination. Well, we can break it up here. What is V2? Or, sorry, what does V out depend on? Well, V out depends on the value of V2. So, what we'll write is V out divided by V2. Now we have a V2 here. Where is V2 on the circuit? V2 is here. You'll notice in a lot of past exam problems they write this kind of V2, and even on the homework. What this means is you put a positive here and a negative at ground. So now what we have is V2 is the voltage across R2. What do we notice though? Well, V2 depends on V in. How so? Well, we have a sort of voltage divider. This is the same voltage across it. So we can put these in parallel. And now this R1 parallel with C1 is in series with R2. So now you have an impedance here and you have a load here. You want to find the load voltage. What you do is you take V2 over V in, and we end up getting V out over V in. What we'll do here is we'll solve for V2 first, the V2 over V in first. Okay, so V2 over V in. V2 over V in, well, let's first break this R1 C1 up. R1 is in parallel with C1, so we'll write it like this, R1 in parallel with C1. And then it's in parallel with, or not parallel, sorry, it's in series with R2. So what we'll draw here is, let's just make a very easy voltage divider. So V2 depends on V in. So the input for this voltage divider is V in. This is all divided by V in, of course. And what we'll notice is that input signal does not matter. We're going to cancel it right away. Now what are we left with? We're left with this voltage divider. Just the components of our circuit. So what we have is we want to find the voltage across R2 divided by R2 plus the parallel combination of R1 and C1. Okay, well that's perfect. We found V2 over V in. Let's simplify this a little more here. So let's move this up. Let's first tackle this R1 parallel with C1. What does that look like? Well, what that looks like is a product over the sum. So we have R1 C1 divided by R1 plus C1. Now we're trying to do this in the phasor domain. Why is that? Well, doing these in the phasor domain just makes more sense. If we were to do this in time domain, it would be disgusting. We would have to do dV/dt over, like, C dV/dt for this capacitor, C dV/dt for this capacitor here. We'd have to find the current through this. It's just kind of a mess. So what we do is we make this into a phasor. So C1 becomes what? 1 over j omega C1. So what we now have is R1 divided by j omega C1 divided by R1 plus 1 over j omega C1. Now this has complex fractions. We have fractions inside of fractions. We don't want that. So what we're going to do is we're going to multiply, I guess we can multiply by what? J omega C1 divided by j omega C1. What that gives us is we can cancel the j omega C1 here with this one. So we're left with R1 divided by j omega C1 gets canceled with this one, so we can write 1 plus j omega C1 times R1. Remember, we have to distribute. So this is what? J omega C1 R1. Perfect. Now we need to plug this back in to this parallel combination, this voltage divider. So what we're going to do is we're going to go here. We're going to plug that in here. We have R2 divided by R2 plus R1 divided by 1 plus j omega C1 R1. And this is our voltage divider now. Alright. Something else that we could definitely do is multiply by 1 plus j omega R1 C1. Which, in this case, we could definitely do. Alright, and that's probably what we should do. Let's multiply top and bottom by 1 plus j omega R1 C1. If y'all don't see this, please let me know here. I'm going to be denoting every step here by an arrow. So we're moving from here to here, and then we're moving down from here to here, making like a little snake. So now we multiply both sides here. We get what? We get R2 times 1 plus j omega C1 R1 on top, divided by, okay, you see how this R2 and R2, they're the exact same. So now what we can do is we can do the same thing, R2 times 1 plus j omega C1 R1 plus, well, we multiply the denominator by itself. Like it's rid of it. So we have plus R1. Bam. Alright. This is as good as it gets here. This is as simplified as it can get. So now what we need to do, let's box this in. We can find V out over V2. So V out over V2. Alright, so let's look here. This is weird, I will say. You have a current source in parallel with a resistor, and then you have this capacitor that shares the current. We have a node here. And we know the current going through R4 is the same current as it's going through C3. These are in series, but we want to find V out. Something you may notice here is, like I said, we have a parallel combination of a current source and a resistor. This should remind you of Norton, the Norton equivalent and Thevenin equivalent. So what we can do is we can remake this circuit, this second stage of our circuit, or output stage. Parallel combination, what does that become? Well, this can become plus minus resistor, capacitor, resistor, and look at this. Hope y'all can follow this. This becomes this here, and now you have one big loop. This is exactly what we need. We have C3, R3. What does the new Thevenin voltage become? Well, we know voltage is equal to current times the resistance or impedance. So what we now have is this GV2 times R3. So we have R3GV2. And now this stays as R4. Now, we are still looking for V out in terms of V in. Right? So now this is just a very easy voltage divider again. We have the voltage across R3 and C2 and C3 in series, and the voltage across R4. So let's create this. We have this voltage divider. Well, the voltage of this is R3GV2. Notice Vin was plus on top, minus on bottom when we kept it as a positive. This one here has the reverse polarity. We have positive on bottom, negative on top. So we have to reverse the sign. The sign. So it's going to be negative. So negative R3 GV2 times, and remember we're dividing by V2. So what we get here now is subtract or get rid of these V2s. We don't have to worry about what actually is being output. Okay, now we have this voltage divider. What do we want to know the voltage across? R4. So we write R4 divided by R4 plus. Plus this series combination. So what is this? R3 plus 1 over j omega C3. Remember, we're going to be using j omega, not S anymore here. And now, what can we do? Well, let's simplify this a little bit. What can we do? Well, let's distribute this negative R3G. Let's get one numerator, whatever, right? Negative R3 R4G divided by, what is this divided by? Well, this is divided by, what, R4 plus R3 plus 1 over j omega C3. What can we do here now? Well, let's multiply top and bottom by j omega. Okay, so let's multiply by j omega C3, I mean, on both top and bottom. Why is that? Well, when we look at poles and zeros, we always want j omega in the, what, numerator? Because we want j omega, or 1 plus j omega over a pole, or 1 plus j omega over a zero. So let's try and get j omega to be on top instead of on bottom. It's kind of difficult to get into the form that we want. So let's multiply it, and what does this give you? This gives you negative R3 R4G j omega C3 on top. Now we distribute this j omega C3 to all three terms. So we get j omega C3 R4 plus j omega C3 R3 plus j omega C3 times 1 over j omega C3 is plus 1. Perfect. And that's what we have here. This is our V out over V2. All right. So I'm going to use another paper here. What we're going to do is we're going to solve for, we're going to multiply them, right? At the very beginning, that's what we needed. We have V out over V2, and we have V2 over Vn. I'm going to rewrite them on this paper here. So what we have is V out over V2 is equal to, what is it equal to? We have negative R3 R4 G times j omega C3 divided by j omega C3 R4 plus j omega C3 R3 plus 1. And then, what can we do? Well, we can forget this. Now we have V2 over Vn. V2 over Vn was just the voltage divider. Well, that was easy. We have R2, 1 plus j omega C1 R1 divided by R2, 1 plus j omega C1 R1 plus R1. Let's multiply them now. So we can get rid of this paper, it doesn't matter anymore. Now we have V out over Vn is equal to those two. So negative R3, R4, I'm going to write this a little quicker. Sorry for the bad handwriting. Divided by, what is this, j omega C3 R4 plus j omega C3 R3 plus 1 times R2, 1 plus j omega C1 R1 divided by R2, 1 plus j omega C1 R1 plus R1. Oh shit, hopefully y'all can see that, my bad. Okay, now this, it looks disgusting, it doesn't look very fun to play with here, but what can we notice? We have a ton of these 1 plus. Remember, we want it in the form of 1 plus j omega over 0 or 1 plus j omega over a pole. That's what we want. This is our form. We need this. So what can we do? Well, we can figure out that I'm going to be using p and z for this type of example. 1 plus p times j omega, this is also equal to 1 plus j omega divided by 1 over p. This is what we're going to be using. We're going to be using this type of equivalent statement a lot. This makes it very easy to go from a very long type of problem here, something like this. It makes it super easy. So, given this, what can we do? Well, let's look here. Or actually, let's look here, actually. It's a little easier. J omega times C3R3. What is that? Well, let's solve it using this. J omega divided by 1 over, what is P? P is C3R3. Really, this isn't 1 over P. 1 over, I guess this is, we can use this as like in. If we have 1 plus P times J omega. J omega over P. This is what we need, right? So we can let P equal to be 1 over N. It makes sense here. Our pole is 1 over C3 R3. Hopefully that makes sense. It's a little weird, but that's correct here. All right. So this makes it very easy for us to solve this. Same thing here. Well, what is this? 1 plus j omega C1 R1. Very easy again. 1 plus j omega 1 over R1 C1. That's 0. What about this here? 1 plus j omega over 1 over R1 C1. Same thing. Now you notice these two are the same. What does that tell us? Well, that tells us this filter has no, well, the zeros and poles will have no effect on it. So the bandwidth is essentially just going to be a flat line. Or not the bandwidth, but your buddy plot for both magnitude and phase. So we're literally just going to have a straight line. For this section here, of course here we have one, we have actually, I guess 2. Technically we don't, we only have 1. But we can rewrite this as j omega over 1 over C3R3. Now, let's take a little closer look at this one. I was using this as an example, but this one is actually true because we have this 1 plus. Let's look a little bit closer at this, and I'm going to rewrite it here towards the bottom. 1 plus j omega C3R4 plus j omega C3R3. We have different resistances. We can't just take it like this, because it can't be 1 plus j omega divided by 1 over C3R4 plus this. We can't do that. So what we need to do is we need to take out something that maybe will make it a little easier for us to deal with. What can we do? What do they share in common? Let's only look at these. What do they share in common? Wow, well, they share in common j omega C3. You notice here, R3 and R4 are the only differences. So let's rewrite this. 1 plus j omega C3 R4 plus R3. Now, do you see here? Look at that. This is going to be like our P. Don't call it actually P, that's not right. It's 1 over this. But now what we can do is we can say 1 plus j omega divided by 1 over C3 R4 plus R3. Wow, it's in that form, 1 plus j omega over a P. over a pole. It's perfect. There we go. We've solved it. So, what do we know? V out over V in is equal to, we keep this here. Something you'll notice whenever you're doing your Bode plot. This is this entire thing here, because it has no poles or zeros. This is your gain. This is, well, not really gain, but your A of omega. And in any case, you would say, you would take the 20 log base 10 of some value, and you would get your some starting point, depending on what other omega value you pick. That's for another day. But for here, we take V out over V in. We can rewrite this A omega, negative R3, R4, G times J omega C3. Now, we can then write this. Wow, this is going to be bad. This is not enough space. Well, we can rewrite this. We can say R2 times what? 1 plus J omega over 1 over R1 C1. Bam. That's our 0. Divided by, well, look, actually keep this. It's perfect. Oh my gosh. We'll keep this here. Bam. But then what do we have? We have, this is only here. This 0. But we have to be careful because we have an R2 and an R1. So what can we do? We can write R1 plus R2 times 1 plus, and then I guess this whole thing here. That goes there. I did not leave myself enough space, but I guess I'll rewrite this. Let me just get a different piece of paper here, if I can find one. Please don't die, man. My phone's not gonna survive. Y'all, this is a crisis. I have no paper on me. Anyways, I hope y'all get that. Let me see if I can rewrite this. Maybe close. Negative R3, R4, G, J omega C3. There we go. This is more space. R2. What is this? 1 plus J omega divided by 1 over R1 C1 divided by, yeah, that's way more space. Okay. So then what we have is R1 plus R2. I hope y'all are seeing where I'm getting this R1 plus R2. I'm moving this R1 over, but we're still getting this plus, and R2 is multiplied to this entire pole. So then what we have is 1 plus J omega divided by 1 over R1 C1 times, remember we multiplied these, we have 1 plus J omega divided by 1 over C3 R4 plus R3. There we go. That's our answer. Yeah, this is terrible. But we have negative R3 R4 G J omega C3, which is our A omega, times R2 R0 1 plus J omega over 1 over R1 C1 divided by 2 poles. R1 plus R2 times this pole, 1 plus J omega, divided by 1 over R1 C1, times 1 plus J omega divided by 1 over C3 R4 plus R3. And that is our answer, V out over V in. So, as you can see here, there was quite a bit of work done, but nothing that we haven't learned. Of course, this is all just algebraic manipulation. I hate this. It's disgusting. I don't like this. I like the way they did that. I mean, Dr. Lip did the test voltage source, whatever. Here it could maybe work if you wanted to do it across this and find RC. But even then, it might be a little difficult because none of us really use it as often. I feel like if you hammer it out, you can definitely do it like this. If you can get comfortable with the algebra, it helps a lot. And you'll pick up sort of these tricks, especially this kind of trick where you put 1 plus j omega, where you know 1 plus p times j omega. You can put it 1 over that. All right, but this was a good question here, especially for anyone that wants practice. Make sure to check out the old exams they sent in the note and resources. It helped a lot going over these old ones. But that's all pretty much. I just wanted to show y'all this, but thanks guys.